Fire on a construction site is a mathematically certain chemical reaction. It occurs automatically whenever optimal environmental conditions are met. Those conditions are defined by the fire triangle. The triangle requires three intersecting elements to initiate combustion: oxygen, fuel, and heat. To remove a single element, the reaction ceases. In the UK, the overarching legal architecture that enforces this scientific control is the Construction, Design and Management Regulations 2015, or CDM. CDM sets explicit requirements for those designing, planning, and carrying out projects. Sites must proactively design out fire risks, provide detection systems, establish clear emergency procedures, and supply appropriate first aid firefighting equipment to protect everyone, including visitors. These rigid requirements must be formalized within the fire safety plan, which forms a core part of the overall construction phase health and safety plan before any operational work begins. Professional site fire safety relies entirely on segregating ignition sources from fuels through strict administrative planning, long before physical walls or barriers are built. Construction introduces numerous active heat sources to a site. Common ignition sources include flames from blowtorches, sparks from welding and grinding, and the highly probable threat of arson. Fuels across a site are grouped into 5 classifications. Class A covers organic solids like timber and cardboard. Class B involves flammable liquids such as fuel oils. Class C covers flammable gases. Class D involves combustible metals, and Class F covers cooking oils. A typical site layout contains all 5. There is also a severe hidden risk associated with welding operations. A leak from an oxygen cylinder can create an oxygen-enriched atmosphere, causing surrounding materials to burn ferociously fast and take workers entirely by surprise. This schematic shows the 4 mechanisms of heat transmission that allow fire to bypass physical distance and spread aggressively through a structure. The first is conduction. Heat energy travels through highly conductive materials, such as copper plumbing pipes or steel trunking, rapidly reaching temperatures high enough to ignite combustibles in adjacent, unseen rooms. Next is convection. Unimpeded, extremely hot combustion gases rise to the ceiling barrier, flowing across the surface and convecting through high-level openings to ignite materials on the opposite side of a room. The third is radiation. An average room fire dissipates up to 3 megawatts of infrared energy. This radiant heat can easily pass through large glass partition walls, igniting nearby structures without any direct flame contact. Finally, there is direct contact, which is the immediate ignition of combustible materials touching a live flame. Routine site activities directly initiate these vectors. An unattended tar boiler can initiate direct contact, while windswept embers from a waste bonfire can easily radiate or conduct heat into nearby structures. Because these heat transmission vectors are invisible and aggressive, relying solely on worker vigilance is insufficient. Controlling them demands engineered administrative systems. Tasks like flame cutting, using bitumen boilers, and grinding are classified as hot work. They are the primary engineered heat threats on site and require a formal permit-to-work system. A hot work permit enforces mandatory constraints. It must be specific to a single task in a clearly identified area, authorize the presence of appropriate fire extinguishers, and account for any adjacent processes involving flammable liquids or gases. The permit specifies a mandatory final fire check at least 1 hour after the work concludes. This delay is critical to catch slow smoldering caused by conduction or convection heating. There is a strict operational rule tied to this check. If trained personnel will not be available to complete this late-day 1-hour inspection, the hot work cannot legally commence. We also use administrative controls to manage the fuel leg of the triangle, particularly highly volatile liquefied petroleum gas, or LPG, like propane and butane. This diagram shows the physics of an LPG leak. The gas operates within a narrow explosive limit of roughly 2 to 10. LPG must be kept above ground, in the open air, on level, compacted surfaces, and completely away from overhead electrical power cables. Minimum separation distances from buildings and boundaries scale by mass. Storing 1,000 kilograms of LPG requires a 3-meter separation distance, while storing 150,000 kilograms mandates a 12-meter separation. Where explosive mixtures of flammable gases or vapors are possible, standard electrical tools cannot be used. Specialized electrical equipment is required. This data table maps the 3 hazard zones against specific electrical protection standards. Zone 0 is an area where an explosive mixture is continually present. Zone 1 is where a mixture is likely to occur under normal circumstances, and Zone 2 is where it is unlikely. Different zones require different protection. XD indicates flame-proof enclosures that contain internal explosions. XI means intrinsic safety, limiting electrical energy so sparks cannot ignite gas. XE indicates increased safety designs that eliminate sparks and hot surfaces entirely. Hot work permits, exact LPG separation distances, and electrical zoning act as invisible administrative firewalls. They physically separate the fuel and heat legs of the fire triangle before a spark ever occurs. Structural compartmentation is the physical method of preventing fire and smoke spread. It works by separating a building into contained zones using fire-resisting walls and floors. On active sites, temporary compartmentation can be quickly achieved by cladding a studded timber frame with 2 layers of skimmed 12.5 mm plasterboard. Once a fire starts, different construction materials fail under severe thermal loads at vastly different but highly predictable rates. Dense timber actually has high fire resistance. As the exterior burns, it produces a predictable charring rate that creates a highly effective insulating barrier, protecting the internal wood. Engineers utilize this predictable char rate through sacrificial timber sizing. They calculate the required char layer into the design, allowing the beam to burn while the core retains its structural stability without sudden collapse. This split-screen graph compares the structural load capacity of a timber beam against a steel joist as ambient temperature increases. Steel has severe thermal vulnerability due to its high thermal conductivity. At exactly 590 degrees Celsius, structural steel loses 2/3 of its strength and begins to immediately sag and twist. The collateral damage of this heat is thermal expansion. At 590 degrees, a 10-meter steel joist will expand 60 millimeters in length. This is sufficient to push out and collapse adjoining brick structures. Other materials fail rapidly as well. Aluminum rapidly loses strength at 200 degrees and melts completely at 660 degrees. Structural concrete relies on steel rebar, which weakens significantly between 400 and 500 degrees. Understanding material physics is critical. When administrative controls fail, the thermodynamic failure rate of the building materials becomes the sole factor dictating how much time workers have to evacuate. Automatic fire alarm systems are the ultimate trigger mechanism for evacuation. Because they are typically installed at the very end of a build, early construction phases rely heavily on manual fire watch procedures and extreme site vigilance. Automatic detectors are engineered to identify one or more of 3 physical characteristics of combustion: smoke, heat, or flame. Smoke detection targets 2 different states of combustion. Ionization detectors sense the small, invisible particles produced early in a fire. Optical detectors sense the physical obscuration or scattering of a light beam caused by visible smoke particles. This matrix links the 3 methods of extinguishment: cooling, smothering, and starving, to specific extinguisher types. Portable fire extinguishers function by directly neutralizing one specific leg of the fire triangle. The cooling mechanism removes heat. Water and water mist extinguishers are highly effective on Class A fires. However, applying standard water to non-polar liquids like petroleum will cause a violent boil-over eruption, ejecting the burning oil. The smothering mechanism removes oxygen. Foam extinguishers float on top of burning liquids to break the interaction between the flame and the fuel surface. Wet chemical extinguishers spray potassium salts that saponify, or turn into a soapy foam layer, over burning cooking oils. The starving mechanism separates the fuel. ABC dry powder melts between 150 and 180 degrees Celsius to form an oxygen-excluding barrier over the fuel. However, this powder is highly acidic and causes severe, unsalvageable corrosion to sensitive electrical equipment. Carbon dioxide extinguishers smother fires by displacing the air entirely. They leave no residue, making them ideal for server rooms and electrical fires. But displacing air creates severe asphyxiation risks for the operator and a high risk of reignition once the gas disperses. Equipment siting is strictly regulated. Hydraulic hose reels must reach within 6 meters of any protected area. Portable extinguishers must be mounted at hand height on escape routes and undergo an annual service program by a competent person. A safe construction site relies on a defense-in-depth strategy. By integrating chemical suppression, the thermodynamic limits of materials, and rigid administrative architecture, we can guarantee that the fire triangle can never sustain itself.